Hi friends, spectroscopy. So spectroscopy is the study of matter and how it interacts with any portion of the electromagnetic spectrum. For our purposes, we're going to be looking at just how it interacts with the visible spectrum, but no, we can look at any of the wavelengths of light that are being released. And we can use this to determine the composition, so what it's made of, the density, how tightly packed the particles are, the temperature, and motion of an object. We can actually use it to see if distant stars or galaxies are moving closer to us or farther away. Bet you didn't know that. Galaxies are actually moving all the time. The universe is expanding. It is never ending, at least from what we know right now. We'll get to that in our next unit. So, spectroscopy, how does it work? Well, we need to use a tool called a spectroscope to study the light. So we have some kind of light source. We have this spectroscope where it will move the light through a small portion and it will hit a prism. A prism is kind of a piece of glass. And what happens is when the light hits the glass, it will split it into different wavelengths. This is actually called refraction. We'll discuss this a little later in our packet. Essentially, is what happens when the light comes in, it starts to bend as it moves through the glass, and because they have different energies and wavelengths, they're going to split at different rates, causing it to have that band of rainbow along the way. So there are 3 different types of spectra: continuous, absorption, and emission. So continuous is just a rainbow, nothing's happening. Absorption and emission spectra are, as you can see, the opposite of each other. Here, I'll move my face so you can see. They are the opposite of each other. So where the dark bands on the absorption spectra are, that is where the colored bands are on the emission. And it all has to do with the energy levels and the distances between them for whatever element you are looking at. So before we move on, let's have a little refresh, trying to figure out where I can put my face. There we go. So I want you to take a moment and I want you to circle the word that best completes each of these sentences. Okay, let's go over it. So when energy is absorbed, it can move an electron up to higher energy levels. You got to take it in order to jump up. As an electron falls to ground state, the lower energy levels, it's going to release energy in the form of a photon or a particle of light. We know red has a long wavelength, low frequency, and a low energy. It's a very lazy wave. Where violet is a short wavelength, high frequency, high energy, very hyper wave. So here we have this image. We can see that there are different energy levels. The electrons are falling the distances down to ground state, level 1, and the falls of the electrons is related to a specific color and wavelength. So go ahead and answer these 2 questions. Is the distance between the energy levels the same? No. We can see that there's quite a bit of a distance between 1 and 2 compared to 3 and 4. Those are closer together. Energy levels farther from the nucleus have a greater energy. We know this from before, but also we can see it because of the wavelength. So the farther away that the electron is falling from, the shorter the wavelength. Short wavelength, hyper, so higher energy. That means the farther away you are, the more energy you have. So we have those 5 different energy levels. What color of light is emitted when the electron is starting in ground state, level 1? What color is emitted by this photon? Or what color photon is emitted by this electron? Took a minute. You confused? Trick question, because nothing's being emitted. The electron's not moving. It's already in the lowest state possible, so no light is going to be emitted from that electron. The farther the fall of an electron, we can see, because I already gave the answer before, the shorter the wavelength of the photon released. The farther the fall, the more energy that's going to be released. More energy, shorter wavelength, high frequency. So how does this all relate to spectroscopy? Well, stars. They're made of different elements depending upon their age. And this is because of different types of fusion reactions happening along the way. The older you are, the more helium you have produced. Once you have enough helium, they can actually start combining with hydrogen to make lithium. You can then have it combine with another hydrogen to start making heavier elements. Fun fact, all of the elements including up to iron, all the elements up to iron that exist in the universe were made through nuclear fusion. We'll talk about what happens heavier than iron in our next unit. So we know that each element has electrons with different distances from the nucleus. It is not the same. Look at our hydrogen and helium. Because they're different distances, they have different energy values. Therefore, different colors of light will be emitted at that point. Oh, look at that. Next slide. Different amounts of energy are released after the electrons fall, causing different colors of light to be emitted. Because they have different distances, each element is unique. We didn't just find some colors and put them on a piece of paper and call it a day. All of these different colors are due to the location of the energy levels. We've just been looking at level 1 through 5. It's the simpler version of it, but there's actually way more than just 5 energy levels within an atom. So we use these unique spectra to identify what stars are made of. These spectra are kind of like our fingerprints. Everybody's fingerprints are different. Fun fact, your fingerprints were made when you were in the womb from touching the tissues around you. So it's unique to everybody because everybody's tissues are unique. So how do we do this? Well, we look at a mixture of what is emitted by an element. We match up the spectral lines then to see if it's present. So here I have element A on its own, element B on its own, and then A and B combined together. Notice the 3 lines in element A are all found in the exact same spot of our mixture. All the lines in element B are found in the exact same spot of our mixture. So this tells me that both element A and B are present within this star. Let's try it out. This is not in your packet, just having a quick conversation. So what I have is the light emitted from a distant star. We are going to determine what elements make this star up. First, let's try helium. So up here is our mixture. Mixture's up here. Notice the first line in helium matches within our mixture. The second line of helium also matches within our mixture. Since both helium lines are up there, it's part of the unknown star. The star can have extra lines. Hear that? The star can have extra lines. The element cannot. Let's try it again. Hydrogen. What do you think? Yep. It's there. So all of the hydrogen lines are found in the unknown star. It's there. What about iron? Yep. Oh, I got way too excited. Yes, all of the lines in iron are present within our unknown star. And what's sulfur? No. As soon as you find one line in the element that's not in the mixture, you're done. Don't have to look any further. You can very clearly see that this line is not present in the mixture. Don't have to search any further. What about oxygen? This is a real obvious one. Nope. We're missing quite a few oxygen lines from within our mixture. So remember, your mixture can have extra lines. Your element cannot. Let's try this checkpoint. Go ahead and take a moment. I want to see if you can determine which elements are found in the mixture. So we have element A, element D, and element Z. This is our mixture. You may find a ruler helpful for lining them up, or you can use your pencil. Little pro tip. Go ahead, try and figure out which elements are there. Oh, did you figure it out? All right, let's see. Take them piece by piece. Element A. Oh, not there. So the first line's not present. Move on. You don't need to keep looking. So element A, not part of it. Let's see. Element D. Yes. Awesome. All the spectral lines of element D are present. So it is in the mixture. Notice the mixture has extra lines. That's okay. We just don't want extra lines in the element. Let's look at element Z. Yep. Bam. All the lines in element Z are present, so it is part of the mixture. There we go. Element A, nope. I found one line. Don't have to look anymore. It is not present. Everything else is there for D and Z. All right. The check-in for spectroscopy will be posted soon. See you later.